In the 1920s, a young German physicist named Werner Heisenberg was struggling. He was trying to understand the strange behavior of electrons inside atoms. In 1925, he retreated to the isolated island of Heligoland in the North Sea to escape a bad case of hay fever. Surrounded by bare rocks and sea, he had a breakthrough. He realized that the classical picture of an electron as a tiny ball with a definite position and a definite speed was wrong. You could know its position or you could know its momentum, but you could never know both perfectly at the same time. The more precisely you measured one, the less you knew about the other. He formulated this in 1927. It became known as the uncertainty principle. It wasn't about faulty instruments. It was a fundamental limit on reality itself. The universe at its core was fuzzy and uncertain. This was a deep defiance of classical logic. It suggested particles don't have properties until they are measured. Many physicists, including Albert Einstein, hated this idea. Einstein famously said, "God does not play dice." He believed there must be some deeper, hidden information that quantum mechanics was missing. He argued that particles must have definite properties all along, we just can't see them. This debate simmered for decades. Then, in 1964, a physicist named John Bell, working at the CERN laboratory in Geneva, devised a mathematical theorem. Bell's theorem was a way to test Einstein's idea. It set up a situation involving two entangled particles. If Einstein's hidden variables were real, the results of measurements on these particles would have to obey a certain statistical limit. If quantum mechanics was right and the weirdness was real, the results would violate that limit. And experiments began in the 1970s. By 1982, a team led by Alain Aspect in Paris had performed a definitive test. The results were clear, Bell's limit was violated, Einstein was wrong. The universe really is that strange. The fuzziness Heisenberg discovered wasn't a local problem. It was woven into the fabric of the cosmos, connecting particles across vast distances in ways that defy all our everyday logic. That defiance is where things truly get interesting. Number 19, the universe is a two-dimensional projection. The universe contains an estimated 2 trillion galaxies. The observable universe stretches 93 billion light-years across. And yet, all the information to describe this immense three-dimensional space might be encoded on a distant, two-dimensional surface. This idea is called the holographic principle. It suggests our reality is a projection, a cosmic hologram. The first clues came from black holes. In the early 1970s, Jacob Bekenstein and Stephen Hawking discovered something strange about black hole entropy, which is a measure of its information content. They found that the information content of a black hole is not proportional to its volume, as you would expect. It's proportional to the surface area of its event horizon, the two-dimensional boundary from which nothing can escape. It was as if all the information about the 3D stuff that fell into the black hole was smeared out on its 2D surface. In 1993, Nobel laureate Gerard Hooft took this idea a step further. He proposed that this principle might apply not just to black holes, but to the entire universe. Leonard Susskind then developed and championed the idea in 1995. The logic is that the maximum amount of information that can be packed into a region of space is defined by its surface area, not its volume. If you try to pack too much information into a volume, it will collapse into a black hole. And the information limit of that black hole is defined by its surface area. This suggests a fundamental limit. The universe itself might have a kind of cosmic event horizon, a boundary far away, and our 3D reality could be a holographic projection of information stored on that boundary. The math behind this is incredibly complex. But a major breakthrough came in 1997 from physicist Juan Maldacena. He discovered a concrete mathematical link, a duality, between a certain type of 3D universe with gravity and a 2D universe on its boundary without gravity. This AD-SCFT correspondence gave the holographic principle a solid mathematical foundation. It showed that at least in some theoretical models, a 3D universe with gravity could be perfectly described by a simpler 2D system. Scientists at Fermilab even ran an experiment called the holometer from 2014 to 2016 to look for evidence of this. They were searching for a kind of fundamental pixelation of spacetime, a blurriness that might exist if our universe is a hologram with a limited resolution. The experiment did not find this blurriness down to the level it could measure, but the idea remains one of the most profound and logical defying concepts in modern physics. All of the depth, all the complexity, all the vastness of the cosmos could be an illusion projected from a flat surface. Number 18, the worst prediction in physics is what drives the cosmos. About 68% of the universe is made of something called dark energy. It's a mysterious force that is causing the expansion of the universe to accelerate, and we don't know what it is, but our best guess connects it to the energy of empty space itself. This is where quantum mechanics enters the picture, and where logic completely breaks down. According to quantum field theory, empty space is not empty at all. It's a bubbling, seething cauldron of virtual particles that pop in and out of existence for fleeting moments. This activity gives the vacuum a certain amount of energy. This is called vacuum energy, and physicists can calculate how much energy the vacuum should have based on quantum theory. The problem is the number they get. When they calculate the expected density of this vacuum energy, the result is staggering. It's about 10 to the power of 120 times larger than the value we actually observe from astronomical measurements of the cosmic expansion. This discrepancy is not a small error. It's not a matter of being off by a factor of 2, or 10, or even a billion. It is a 1 followed by 120 zeros. This is widely considered the single worst theoretical prediction in the history of physics. It's so wrong, it's almost comical. To put this number in perspective, the number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. The prediction is wrong by a factor that is vastly larger than the number of atoms in everything we can see. This is known as the cosmological constant problem, or the vacuum catastrophe. Einstein originally proposed a cosmological constant in his theory of general relativity to keep the universe static, a sort of built-in anti-gravity. When he learned the universe was expanding, he called it his biggest blunder. But in 1998, astronomers discovered the expansion was accelerating, and the cosmological constant was revived as the simplest explanation for dark energy. The measured value of this constant is tiny, but the value predicted by quantum mechanics is enormous. If the vacuum energy were as large as quantum theory predicts, its repulsive force would be so strong that it would have ripped the universe apart moments after the Big Bang. Stars and galaxies would have never formed, we would not be here, so why is there this colossal mismatch? Nobody knows. It is one of the deepest mysteries in science. It tells us that our two best theories of the universe, quantum mechanics and general relativity, are fundamentally incompatible. Something is profoundly wrong in our understanding of how gravity and the quantum world interact on a cosmic scale. Number 17. The past can be influenced by the future. In 1978, the physicist John Wheeler proposed a thought experiment. It was a variation of the famous double-slit experiment, which shows that a single particle, like a photon, can behave as both a particle and a wave. In the standard experiment, if you watch which slit the photon goes through, it acts like a particle and goes through one or the other. If you don't watch, it acts like a wave, goes through both slits at once, and creates an interference pattern. Wheeler's version added a cosmic twist. He called it the delayed choice experiment. Imagine a photon traveling from a distant quasar billions of light years away. On its way to Earth, it passes a massive galaxy that acts as a gravitational lens. The galaxy's gravity can bend the photon's path, so it could reach us by taking a path around the left side of the galaxy or the right side. This is like a cosmic double-slit experiment. The galaxy is the screen with two slits. Here is the strange part. We on Earth can choose how to observe the photon after it has already passed the galaxy billions of years ago. We can set up a telescope to detect which path the photon took. In that case, we will find it took either the left path or the right path. It behaved like a particle, or we can set up a different kind of detector, one that recombines the two paths and looks for an interference pattern. If we do that, we will find an interference pattern. This means the photon must have traveled both paths at once, like a wave. The choice we make in the present seems to determine how the photon behaved billions of years in the past. It's as if our measurement today reaches back in time and changes the history of the particle. This doesn't mean we can send messages to the past or create time paradoxes. The results are only revealed once the entire experiment is complete. But it defies our classical sense of cause and effect. The cause, our measurement choice, happens long after the effect, the photon's journey around the galaxy. Real versions of this experiment have been carried out in laboratories since the 1980s, using mirrors and beam splitters instead of galaxies. The first was conducted by Carroll Alley and his team at the University of Maryland in 1984. Every single time, the results confirm Wheeler's prediction. The choice of what to measure, even when delayed, seems to retroactively determine the particle's past state. The universe on a quantum level doesn't seem to have a definite history until it is observed. The past is not fixed. It is as uncertain as the future until a measurement is made. Number 16, an empty vacuum weighs something. Empty space is not nothing. It has a physical property that can be measured. This property is called the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir was working at Philips Research Labs. He was studying the forces between colloid particles. He stumbled upon a strange quantum prediction. According to quantum theory, the vacuum is filled with electromagnetic waves of all possible wavelengths, constantly fluctuating. These are the same virtual particles that contribute to the vacuum energy. Casimir realized that if you place two uncharged, perfectly conducting metal plates very close together in a vacuum, some of these waves won't fit between the plates. The waves with a wavelength longer than the distance between the plates are excluded. However, the full spectrum of waves can still exist on the outside of the plates. This means there is more pressure from the quantum fluctuations on the outside of the plates than on the inside. This imbalance creates a tiny, attractive force, pushing the plates together. This force is not a chemical bond or a gravitational pull. It is a force from nothing, a direct consequence of the quantum nature of the vacuum. The effect is extremely small and only measurable at very short distances. For a long time, it was just a theoretical curiosity. Measuring it was incredibly difficult because the plates have to be perfectly smooth and parallel, and other forces like electrostatic attraction can interfere. But in 1997, Steve Lamoureux at the University of Washington finally measured the Casimir force with a precision of about 5%. He used a torsion pendulum to measure the tiny force between a spherical lens and a flat plate. Subsequent experiments have confirmed the effect with even greater accuracy. The Casimir effect is real. This has huge implications for cosmology. It is direct experimental proof that the vacuum of space has energy and can exert pressure. This is the very same vacuum energy that is believed to be driving the accelerated expansion of the universe as dark energy. While the cosmological constant problem shows our calculations are wildly wrong, the Casimir effect shows the basic idea is right. An empty space has a weight. It's not a static, empty stage for the universe to perform on. It is an active participant. On a cosmic scale, the cumulative effect of this nothingness is the most powerful force in the universe, pushing galaxies apart and determining the ultimate fate of the cosmos. Number 15, the universe should not be here at all. The Big Bang created matter and antimatter in almost perfectly equal amounts. For every particle, like an electron, there was an antiparticle, a positron. They are identical in mass but have opposite charges. When a particle and its antiparticle meet, they annihilate each other in a flash of energy. You know, if the universe started with perfect symmetry, with an exactly equal amount of matter and antimatter, then everything should have annihilated everything else. The early universe would have been a sea of intense radiation, and as it expanded and cooled, it would have been left with nothing but a dilute bath of photons. There would be no matter, no stars, no galaxies, no planets, no people, but we are here. The universe around us is made almost entirely of matter. So where did all the antimatter go? This is one of the biggest unsolved problems in physics, known as the baryon asymmetry problem. Somehow, there must have been a slight imbalance in the very early universe. For every billion antiparticles, there must have been about 1,000,000,001 particles of matter. After all the annihilation was over, that tiny one in a billion surplus was left over to form everything we see today. What caused this crucial imbalance? In 1967, the Soviet physicist Andrei Sakharov proposed a set of 3 conditions that would be necessary for this to happen. First, the process must violate something called baryon number conservation. This means there must be a way to create more matter than antimatter. Second, it must violate C-symmetry and CP symmetry. C-symmetry means the laws of physics should be the same if you swap a particle with its antiparticle. CP symmetry is a combination of that and swapping its spatial coordinates like a mirror image. Experiments have actually observed CP violation. It was first discovered in the decay of particles called kaons in 1964 by James Cronin and Val Fitch, who won the Nobel Prize for it. However, the amount of CP violation we have measured in our particle accelerators is far too small to account for the huge imbalance we see in the cosmos. There must be other unknown sources of this asymmetry. The third condition Sakharov proposed is that the universe must have gone through a period out of thermal equilibrium. This is provided by the rapid expansion of the universe itself. So, while we have a theoretical framework, we are missing the key ingredient. We haven't found the specific particle interactions that could create matter with such efficiency. The very existence of a cosmos filled with galaxies, rather than empty radiation, defies our standard model of particle physics. It points to some new physics, some unknown process that occurred in the first fraction of a second of the universe's existence, a process that broke the symmetry and allowed our world to exist. Number 14, information can never be destroyed, but black holes destroy it. One of the most fundamental principles of quantum mechanics is called unitarity. It essentially says that information is never lost. If you know the complete quantum state of a system at one point in time, you can, in principle, calculate its state at any other point in time, past or future. The information about the system is always preserved. It might get scrambled and hard to read, like burning a book. The information in the book isn't truly gone, it's just been transformed into the complex state of the ash, smoke, and heat. A sufficiently powerful computer could, in principle, reverse the process and reconstruct the original book. Information is conserved, then come black holes. In the 1970s, Stephen Hawking made a shocking discovery. He combined quantum mechanics with general relativity and found that black holes are not completely black. They slowly leak radiation, now called Hawking radiation. This radiation is thermal, meaning it is random and carries almost no information about what fell into the black hole. Over an immense amount of time, a black hole will completely evaporate, leaving behind only this featureless thermal radiation. This creates a paradox. What happens to the information of all the things that fell into the black hole? If a star with a complex structure and history collapses to form a black hole, and that black hole then evaporates into random thermal radiation, where did the information about the star go? It seems to have been completely erased from the universe. This violates the principle of unitarity. This is the black hole information paradox. It pits our two pillars of modern physics against each other. General relativity describes the black hole and its event horizon, from which nothing, not even information, can escape. And quantum mechanics insists that information can never be lost. For decades, physicists have been trying to solve this. Hawking himself initially believed the information was lost, a controversial stance. He later changed his mind in 2004, conceding that the information must get out somehow. But how? Some theories propose the information is stored on the event horizon, consistent with the holographic principle. Others suggest it leaks out subtly encoded in the Hawking radiation in ways we don't yet understand. Still others propose bizarre objects like firewalls at the event horizon that would destroy anything falling in. The paradox is not just an academic puzzle. It forces us to confront the limits of our current theories. Resolving it will likely require a full theory of quantum gravity, a theory that can describe how space-time and matter behave in the most extreme environments in the universe. It challenges the very foundation of how we believe reality works. Number 13, the universe is too perfect. The universe is incredibly flat. When cosmologists say flat, they are talking about the geometry of space-time on a large scale. According to Einstein's general relativity, mass, and energy curve spacetime, the overall shape of the universe can be one of three things closed, like the surface of a sphere open, like the surface of a saddle, or flat, like a sheet of paper. A closed universe would eventually stop expanding and collapse back on itself in a big crunch. An open universe would expand forever. A flat universe is the critical, perfectly balanced case, also expanding forever, but with the expansion rate slowing down over time. Our best measurements from the cosmic microwave background radiation show that the universe is astonishingly flat. The deviation from perfect flatness is less than 0.4%. This presents a huge problem. A flat universe is an unstable state, like balancing a pencil on its point. Any tiny deviation from perfect flatness in the early universe would have been massively amplified as the universe expanded. For the universe to be so close to flat today after 13.8 billion years of expansion, it must have started out with an unimaginable degree of flatness. The initial density of the universe had to be fine-tuned to the critical density to an accuracy of about 1 part in 10 to the power of 62. This is the flatness problem. Why was the early universe so perfectly balanced? Relying on sheer luck is not a satisfying scientific explanation. The most widely accepted solution to this problem is cosmic inflation, proposed by Alan Guth in 1980 and developed by others like Andre Linde and Paul Steinhardt. Inflation theory suggests that the universe went through a period of hyper-accelerated exponential expansion in the first tiny fraction of a second after the Big Bang. This expansion was driven by a quantum field called the inflaton field. This period of inflation would have stretched any initial curvature of the universe to such an enormous scale that our observable universe would appear practically flat, just as a small patch on the surface of a giant balloon looks flat to an ant walking on it. The inflation theory is very successful. It not only solves the flatness problem, but also another major puzzle called the horizon problem, which asks why distant parts of the universe look so similar. But inflation itself is a quantum process on a cosmic scale that defies logic. It proposes that a quantum field in a specific state generated a repulsive gravity that blew up the universe by a factor of at least 10 to the power of 26 in less than a trillionth of a second. It created our entire vast, flat cosmos from a subatomic-sized patch of space. It's a wild idea, but it's the best one we have to explain the unnerving perfection of the universe's geometry. Number 12, galaxies are held together by particles that shouldn't exist. About 85% of the matter in the universe is not the normal matter that makes up stars, planets, and us. It's something called dark matter. We can't see it. It doesn't emit, reflect, or absorb light. but we know it's there because we can see its gravitational effects. The first evidence came in the 1930s from the Swiss astronomer Fritz Zwicky. He was studying the Coma cluster of galaxies and noticed that the galaxies were moving so fast that the cluster should be flying apart. The gravity from the visible matter wasn't nearly enough to hold it together. He proposed there must be some dunkel materie, or dark matter, providing the extra gravitational glue. His ideas were largely ignored for decades. Then, in the 1970s, the astronomer Vera Rubin provided undeniable evidence. She was studying the rotation of spiral galaxies. According to Newtonian physics, stars far from the galactic center should orbit more slowly than stars closer in, just like the outer planets in our solar system orbit the sun more slowly than the inner ones. But Rubin found that the stars in the outer regions of galaxies were moving just as fast as the ones in the inner regions. The galaxies were spinning too fast to hold themselves together. The only way to explain this was if each galaxy was embedded in a massive, invisible halo of dark matter, providing the extra gravity needed. Since then, evidence for dark matter has poured in from many sources, including gravitational lensing, the cosmic microwave background, and the structure of galaxy clusters. The cosmic map is shaped by this invisible substance, but what is it? This is where quantum mechanics comes in, and the logic gets strange. The standard model of particle physics, our incredibly successful theory of all known particles and forces, has no room for dark matter. None of the particles we know, electrons, protons, neutrons, neutrinos, d, can be the dark matter particle. It has to be something new, something completely outside our current understanding. The leading candidates are hypothetical particles called WIMPs, or weakly interacting massive particles. These would be heavy particles that only interact through the weak nuclear force and gravity, which would explain why they are so hard to detect. And scientists are running huge experiments deep underground, like the Xenon and Liu X experiments, trying to catch the rare collision of a WIMP with a normal atom. So far, they have found nothing. Other candidates include actions, which are extremely light, hypothetical particles, or even primordial black holes formed in the early universe. The existence of dark matter on a cosmic scale means that the quantum world is far larger and stranger than we thought. The majority of matter in the universe is made of particles that our best theories say shouldn't exist. The universe is built from a type of substance that remains a complete mystery. Number 11, the universe started by breaking the rules of energy conservation. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed from one form to another. This is a cornerstone of physics, but the Big Bang itself appears to be a flagrant violation of this law. How can a universe full of energy and matter, about 10 to the power of 54 kilograms of mass energy, appear from nothing? On a quantum level, energy conservation can be temporarily violated. The uncertainty principle, the same one discovered by Heisenberg, also applies to energy and time. It means that over very short time intervals, the amount of energy in a system can be uncertain. This allows for the creation of virtual particles that pop out of the vacuum and annihilate each other very quickly. This is a well-tested part of quantum mechanics, but could the whole universe be a giant quantum fluctuation? This idea that the universe began as a fluctuation in a pre-existing vacuum or nothingness was proposed by physicists like Edward Tryon in 1973. He famously quipped, "Our universe is simply one of those things which happen from time to time." The idea gains more ground when you consider the total energy of the universe. The matter and radiation in the universe have positive energy, but gravity has negative energy. Gravitational potential energy is negative because you have to add energy to pull two massive objects apart. In a perfectly flat universe like the one we appear to live in, the positive energy of all the matter and radiation might be perfectly balanced by the negative energy of gravity. The total energy of the universe could be exactly zero. If the total energy is zero, then you don't need any energy to create it. It could have appeared from nothing without violating the conservation of energy. This ultimate free lunch hypothesis is supported by the theory of cosmic inflation. During inflation, the rapid expansion of space created vast amounts of positive energy in the form of matter and radiation. At the same time, it created a correspondingly vast amount of negative gravitational energy. The inflating field essentially borrowed energy from the gravitational field to create particles. So, the universe could have started from an incredibly tiny patch of vacuum with near zero energy, and through a quantum tunneling event, initiated a period of inflation that created the entire cosmos while keeping the total energy budget at zero. This is a universe born from a loophole in the laws of physics, a cosmic scale version of something from nothing. It is a profound defiance of our everyday logic, where the greatest event in history was not the creation of energy, but the separation of positive and negative energy from an initial state of nothing. Number 10, particles are connected instantly across billions of light years. This is the phenomenon that Albert Einstein called spooky action at a distance. It's called quantum entanglement. When two or more particles are created in a certain way, their quantum states can become linked. They are described by a single shared wave function. From that moment on, they behave as a single system, no matter how far apart they are. If you measure a property of one particle, like its spin, you instantly know the corresponding property of the other particle. For example, if two entangled particles are created with a total spin of 0, and you measure one to have a spin up, you will know with 100% certainty that the other particle, at that exact same moment, will have a spin down, even if it's on the other side of the galaxy. This connection is instantaneous. It appears to happen faster than the speed of light, which violates Einstein's principle of locality, the idea that an object is only directly influenced by its immediate surroundings. Einstein and his colleagues Boris Podolsky and Nathan Rosen proposed this as a thought experiment in 1935, the EPR paradox, to argue that quantum mechanics must be incomplete. They believe the particles must have had predetermined hidden variables from the moment they were created, like a pair of gloves separated into two boxes. Opening one box and seeing a left-handed glove instantly tells you the other is right-handed, but there's nothing spooky about it. The information was always there, but as John Bell's theorem and subsequent experiments proved, this is not the case. The universe is non-local. The properties of the particles are not determined until the moment of measurement. The act of measuring one particle seems to instantly influence the state of the other, no matter the distance. This doesn't allow for faster than light communication because the outcome of the measurement on the first particle is still random. You can't force it to be spin up to send a message. You can only discover its state, and in doing so, know the state of its partner. But the correlation is perfect and instantaneous. On a cosmic scale, this is mind-boggling. The particles created in the Big Bang or in distant quasars could still be entangled today. An event in one part of the universe, like a measurement made by an alien civilization on a particle, could have an instantaneous, albeit subtle and non-communicative, connection to a particle in our own galaxy. The universe is not a collection of separate objects. It is a deeply interconnected, holistic system linked by these spooky, non-local quantum threads that defy our classical notions of space and time. Number 9, the universe may split into infinite copies of itself every second. The act of measurement in quantum mechanics is deeply problematic. According to the standard theory, a quantum system, like an electron, exists in a superposition of all possible states at once. Its wave function describes the probabilities of finding it in any given state. When you measure it, the wave function inexplicably collapses, and the electron is found in just one of those states. But what causes this collapse and what counts as a measurement? Does it require a conscious observer? This is the measurement problem. In 1957, a young physicist named Hugh Everett III, in his PhD thesis at Princeton, proposed a radical solution. He suggested that the wave function never collapses at all. Instead, at the moment of measurement, the entire universe splits. For every possible outcome of the measurement, a new parallel universe is created. In one universe, you measure the electron's spin as up. In another identical universe, a copy of you measures the electron's spin as down. This is the many worlds interpretation MWI of quantum mechanics. It takes the mathematics of the theory at face value. There is no special process for measurement. There is just the smooth, continuous evolution of the universal wave function. Every quantum interaction, every superposition leads to a branching of reality. This means that every time a radioactive atom could decay, the universe splits into a world where it did and a world where it didn't. Every time a photon hits a semi-transparent mirror, the universe splits into a world where it passed through and a world where it was reflected. The number of parallel universes created would be staggeringly large, constantly branching into a near-infinite multiverse. In this view, our reality is just one branch of an unimaginably vast and complex tree of universes. Every possible outcome of every event exists somewhere in this multiverse. There are universes where you chose a different career, where the dinosaurs were never wiped out, where the laws of physics might even be slightly different. While there is no way to test this idea directly, as the parallel worlds are, by definition, causally disconnected from ours, it is taken seriously by many physicists. It is a clean, logical solution to the measurement problem, even if its implications are profound. It suggests that the cosmos is infinitely larger than we can ever observe, and that countless versions of our own history are playing out in parallel realities. Number 8, stars are powered by a quantum trick. The sun, like all stars, generates energy through nuclear fusion. In its core, where the temperature is about 15 million degrees Celsius and the pressure is immense, hydrogen nuclei protons are fused together to form helium. This process releases a tremendous amount of energy which powers the sun and ultimately supports life on Earth. But there is a problem. According to classical physics, this shouldn't happen. The protons in the sun's core are all positively charged. Like, charges repel each other. This electrostatic repulsion creates a huge energy barrier called the Coulomb barrier. For two protons to get close enough to fuse, they need to overcome this barrier. The temperature in the sun's core, while incredibly hot, is not nearly hot enough to give the protons enough kinetic energy to smash through this barrier. The average proton in the sun's core has only about 1/1000th of the energy required to overcome the repulsion. So, how does the sun shine? The answer is a purely quantum mechanical phenomenon called quantum tunneling. On a quantum scale, particles don't have a definite position. They are described by a wave function that represents the probability of finding them somewhere. This probability wave doesn't just stop at a barrier, it decays exponentially, but a tiny part of it extends through the barrier. This means there is a small but non-zero probability that a particle can simply appear on the other side of a barrier that it classically does not have the energy to cross. It's like throwing a rubber ball at a wall and having it suddenly appear on the other side. In the sun's core, even though a single proton doesn't have enough energy to overcome the Coulomb barrier, the sheer number of protons and the vast timescale means that quantum tunneling happens constantly. Two protons will approach each other, and while classical physics says they will always repel, quantum mechanics allows for a tiny chance that they will tunnel through the barrier and get close enough for the strong nuclear force to take over and bind them together. This is the first step in the proton chain reaction that powers the sun. Without quantum tunneling, the sun and all the stars in the universe would not be able to ignite. The cosmos would be dark and cold. The very existence of starlight is a testament to this bizarre quantum trick that allows particles to break the classical rules and be in a place they have no right to be. Number 7, most particles in the universe might be their own antiparticles. We know that every particle has an antiparticle. An electron has a positron. A proton has an antiproton. They have the same mass but opposite charge, but in 1937, the Italian physicist Ettore Majorana proposed a theoretical possibility. He suggested that there could be a class of particles that are their own antiparticles. These are now called Majorana fermions. Of all the known fundamental particles in the Standard Model, only one could potentially be a Majorana particle, the neutrino. Neutrinos are ghostly, incredibly light particles that interact very weakly with other matter. Trillions of them are passing through your body every second, mostly from the sun. They have no electric charge, which is a necessary condition for a particle to be its own antiparticle. If neutrinos are Majorana particles, it could have profound consequences for cosmology. It could help explain the baryon asymmetry problem, the mystery of why there is so much more matter than antimatter in the universe. A theoretical process called leptogenesis suggests that in the very hot early universe, heavy Majorana neutrinos could have decayed in a way that produced slightly more leptons, like electrons, than antileptons. This lepton asymmetry could have then been converted into the baryon asymmetry we see today. So, are neutrinos their own antiparticles? Scientists are trying to find out. The key experiment to test this is to look for a hypothetical type of radioactive decay called neutrinoless double beta decay. In normal double beta decay, a nucleus decays by emitting 2 electrons and 2 antineutrinos. This is a very rare but observed process. If neutrinos are Majorana particles, then a nucleus could decay by emitting 2 electrons and no neutrinos. The 2 antineutrinos that would normally be emitted would essentially annihilate each other inside the nucleus because they are the same particle. This process would be even rarer. Experiments like Gerda in Italy and EXO 200 in the United States are using large amounts of specific isotopes deep underground, shielded from cosmic rays, to look for this specific decay signature. So far, it has not been observed. But if it is ever detected, it would be a monumental discovery. It would mean that neutrinos, one of the most abundant particles in the cosmos, are made of this strange Majorana substance. It would confirm the existence of a new type of matter and provide a powerful clue to solving the mystery of our own existence. Number 6, space-time itself is not smooth, but a foaming sea of possibilities. On a large scale, Einstein's general relativity describes space-time as a smooth, continuous fabric. But at the smallest possible scales, things get much weirder. At the Planck length, which is an incredibly tiny 10 to the power of 35 meters, quantum mechanics is expected to take over. At this fundamental level, space-time itself is thought to be subject to the uncertainty principle. The geometry of space and time would no longer be well defined. Instead, it would be a seething, chaotic quantum foam. This idea was first proposed by John Wheeler in 1955. He suggested that at this tiny scale, the energy fluctuations of the vacuum would be so enormous that they would warp and twist the fabric of space-time violently. Tiny bubbles and wormholes would be constantly forming and disappearing in a probabilistic froth. Space-time would not be a static background, but a dynamic, turbulent entity. In this quantum foam, the very concepts of here and there, before and after, would lose their meaning. The smooth geometry of Einstein's theory would be an approximation, something that only emerges when you average over larger distances and times. It's like the surface of the ocean. From a satellite, it looks smooth. But up close, it's a chaotic mess of waves and foam. This has profound implications. For one, it sets a fundamental limit on the precision with which we can measure distances. You can't measure a distance smaller than the Planck length, because space-time itself is fluctuating at that scale. It also suggests that virtual black holes could be popping in and out of existence in the quantum foam. These tiny short-lived black holes would scramble information and could have effects on particle physics. The concept of quantum foam is still theoretical. We have no way to directly probe the Planck scale with our current technology. But it is a logical consequence of trying to combine quantum mechanics and general relativity. It tells us that the reality we perceive, with its stable and predictable dimensions of space and time, is an illusion. The fundamental nature of the cosmos is a chaotic, probabilistic foam where the rules of geometry and causality break down completely. Number 5, the end of the universe could be triggered by a quantum event. The vacuum of our universe might not be truly stable. According to quantum field theory, the Higgs field, which gives particles their mass, has a certain potential energy. Our universe currently exists in a state where the Higgs field has a particular value. We assume this is the lowest possible energy state, a state of true vacuum, but it's possible that this is not the case. There could be another, even lower energy state available. Our universe might be living in a false vacuum. A false vacuum is metastable. It's like a ball resting in a small dip on the side of a large hill. It's stable for now, but if it gets a big enough push, it can roll over the edge and fall to a much lower, more stable state at the bottom of the hill. For the Higgs field, this push could come from a random quantum fluctuation. A tiny bubble of the true vacuum could spontaneously appear somewhere in the universe through quantum tunneling. This bubble would have different physical laws. The value of the Higgs field inside would be different, meaning the masses of all fundamental particles would change. This bubble of true vacuum would be at a lower energy state, so it would be catastrophically stable. It would expand outwards at the speed of light, converting the false vacuum of our universe into the true vacuum. The bubble wall would be a sphere of pure energy that would destroy everything in its path. We would have no warning. Because it travels at the speed of light, we wouldn't see it coming. One moment, our universe exists. The next, it is replaced by a new kind of universe with different physics. This scenario is called vacuum decay. Whether this can actually happen depends on the precise masses of the Higgs boson and the top quark. Current measurements from the Large Hadron Collider suggest that our universe is very close to the line between stable and metastable. It seems to be perched right on the edge. While the timescale for such a random event to happen anywhere in our observable universe is predicted to be incredibly long, possibly longer than the current age of the universe, it's not zero. The ultimate fate of the cosmos might not be a slow cooling or a fiery crunch, but a sudden, violent end triggered by a single random quantum event that rewrites the laws of physics. Number 4. Reality is a consensus reached by quantum systems. What does it mean for something to be real or objective? We usually think it means that its properties exist independently of who is observing it. But a new line of reasoning in quantum mechanics challenges this idea. A thought experiment proposed in 2018 by Daniela Frautschiger and Renato Renner, building on earlier work by Eugene Wigner, shows that in a quantum world, different observers can come to logically contradictory conclusions about the same event. It's a complex scenario involving multiple observers, entangled particles, and quantum measurements. In essence, it shows that if you apply the rules of quantum mechanics consistently, you can create a situation where one observer concludes a measurement had a certain outcome, while another observer, who treats the first observer as a quantum system, concludes it had a different outcome. And both of them are correct according to the theory. This suggests that there may be no single objective reality. Facts might be relative to the observer. This idea is sometimes called cubism or quantum Bayesianism. It interprets the probabilities in quantum mechanics not as objective features of the world, but as the subjective degrees of belief an agent has about the outcomes of measurements. The wave function is not a real thing out in the world. It's a mathematical tool that an observer uses to make predictions. In this view, reality is not something that is independently out there. It is something that is brought into being through the act of interaction or measurement. The universe is participatory. On a cosmic scale, this is a radical departure from classical thinking. It implies that the universe doesn't have a set of pre-existing properties that are simply waiting for us to discover them. The properties of a distant star or galaxy might not be definite until they interact with something, until their information reaches us and a measurement is made. The shared reality we experience is a kind of consensus, a network of consistent information established through countless quantum interactions. The idea of a single God's eye view of the entire cosmos with all its properties laid out might be a fundamentally flawed concept. Number 3, time may not be a fundamental feature of the universe. In our everyday experience, time is fundamental. It flows relentlessly forward, separating the past from the future. But in physics, time's role is more ambiguous. In Einstein's relativity, time is woven together with space into a single entity, space-time. But in quantum mechanics, time is treated differently. It's not an observable property of a system like position or momentum. It's a background parameter, a clock that just ticks away. When you try to combine these two theories to create a theory of quantum gravity, time often disappears from the equations altogether. The most famous example of this is the Wheeler-DeWitt equation, formulated in the 1960s by John Wheeler and Bryce DeWitt. It is an attempt to write down the wave function for the entire universe, but the equation has no time variable in it. It describes a static, timeless universe. This is the problem of time in physics. If the fundamental reality of the universe is timeless, where does our powerful perception of the flow of time come from? One idea is that time is an emergent property. It's not fundamental, but it arises from the quantum relationships between different parts of the universe. In this view, the universe is a vast, static quantum state. What we perceive as time is just the unfolding of correlations within this state. A clock doesn't measure a fundamental flow of time. A clock is just a physical system whose state is correlated with the state of other physical systems. Our brains, our memories, the very process of cause and effect could all be patterns within this timeless quantum reality. Another related idea connects the arrow of time to quantum entanglement. Some physicists propose that the entanglement between different parts of the universe is always increasing. This increasing entanglement could be what gives time its direction. The past is a state of lower entanglement, and the future is a state of higher entanglement. The universe, at its most basic level, might not be a story that unfolds in time. It might be a single timeless quantum object, and our experience of a dynamic, evolving cosmos is a perspective that emerges from the intricate web of quantum correlations within it. Number 2, the structure of the universe was seeded by quantum noise. The universe is not uniform. It is filled with a vast cosmic web of galaxies, clusters, and superclusters separated by giant voids. Where did all this structure come from? If the early universe was perfectly smooth, it should have stayed that way as it expanded. The answer, according to our best cosmological model, is that the seeds of all cosmic structure were planted by quantum mechanics. The theory of cosmic inflation proposes that the universe underwent a period of incredibly rapid expansion in its first moments. During this inflationary epoch, the universe was dominated by a quantum field called the inflaton. Like all quantum fields, the inflaton field was subject to the uncertainty principle. It was constantly experiencing tiny, random quantum fluctuations. It was a sea of quantum noise. Normally, these fluctuations happen on a subatomic scale and average out to nothing. But during inflation, the expansion of space was so fast and so extreme that it took these microscopic quantum fluctuations and stretched them to astronomical sizes. Tiny subatomic ripples in the quantum field were blown up to become vast fluctuations in the density of energy across the universe. Regions that were slightly denser became the seeds for future galaxies and galaxy clusters. Regions that were slightly less dense became the cosmic voids. When inflation ended, these density fluctuations were frozen into the fabric of space-time. They left an imprint on the cosmic microwave background CMB, the afterglow of the Big Bang. We can see these imprints today as tiny temperature variations in the CMB map. The Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite have measured these variations with incredible precision. The statistical properties of these temperature fluctuations match the predictions of inflation perfectly. This is one of the strongest pieces of evidence for the theory. It is a direct link between the quantum world and the largest structures in the cosmos, every galaxy, every star, every planet, and ultimately we ourselves owe our existence to random quantum jitters in the first fraction of a second of the universe's life. The entire cosmic web is a fossilized record of quantum noise. Number 1, the universe is not locally real. This brings us back to where we started, with the core defiance of quantum mechanics, confirmed by Bell's theorem. The universe is not locally real. This is a combination of two common sense ideas. Locality is the idea that distant objects cannot instantly affect each other. Any influence must travel at or below the speed of light. Realism is the idea that objects have definite properties, whether we are measuring them or not. A planet has a definite position even when no one is looking at it. Quantum mechanics, through the phenomenon of entanglement and the violation of Bell's inequalities, tells us that at least one of these assumptions must be wrong. Or possibly both. The experiments, starting with Alain Aspect in 1982 and continuing with more and more sophisticated Loophole-free tests, like the one at Delft University of Technology in 2015, have confirmed this beyond any reasonable doubt. The universe obeys quantum mechanics, not our classical intuition. So, what does it mean for the cosmos to not be locally real? It could mean that realism is false. Particles do not have definite properties until they are measured. The universe is fundamentally indeterminate, and the act of measurement helps create the reality it measures. This is the standard Copenhagen interpretation, or it could mean that locality is false. There are connections that operate faster than light, like the spooky action at a distance of entanglement. This doesn't mean we can send signals faster than light, but it means the universe is interconnected in a way that transcends our normal understanding of space. Or it could be something even stranger, a breakdown of both concepts. This is not just a philosophical point. It is a hard experimental fact about the nature of the cosmos. It means that the fundamental logic we use to navigate our daily lives simply does not apply to the underlying reality of the universe. The cosmos is not a giant clockwork machine, as Newton thought. It is a probabilistic, interconnected, and indeterminate system where observation plays a key role in shaping reality and where connections can defy the limits of space. This is the ultimate defiance of logic, a truth about the universe that forces us to abandon our most deeply held intuitions about how the world is supposed to work.